of us together. Right, let's begin. Right, hopefully this does record. Okay, so we are now on cognitive. I hope you guys have been following along where we are. Okay, everything does match very nicely with your reading in your textbook. Okay, so we're on this part now, the alcohols. Got it? Alcohol reactions. You already understand a lot about what alcohols are, at least how they're made and the naming of alcohols. So all we're really looking at here, okay, is really the reactions that you need to remember and to show them on the test, all right? Okay, so now in university level, you actually have a lot of alcohols that you will be need to be familiar with. Okay, if you guys go on to be doctors or whatever later, you'll learn the rest of these. But for IB standard level, we only really care about combustion, oxidation, and esterification, which is the making of esters. Okay, that's all we really need to get for standard level, right? So anyways, recall that alcohols, okay, have your hydroxy functional group. Sorry, I spelled it wrong. And you know that it's polar, right? So yeah, and that increases its solubility in the water, okay? What is the class name of this again? Remember from that other video I sent you? The class name is what? Alcohols, right? But the functional group is hydroxy, right? HYDROXYL, okay? So I think I can't spell that right, but anyway, so the first one that we need to worry about is combustion reaction. Okay, so that is very similar to what you saw with combustion of alkanes. Okay, so you're still making your main products of carbon dioxide and water. Okay, and of course, when you have to balance this, so first off, on a test, you would be given just like a sentence, something like this: write the equation for the combustion of ethanol. And you would have to write that all from scratch on your own, okay? So you need to know how to write a proper formula for your alcohols before you can actually do your balance equation. And then, of course, just like we did with the alkanes, you still follow the rule of the Korean person's last name, Cho, okay? C, then H, then O. So this one comes out nicely. I don't think there are going to be any decimals or fractions. If you remember in that video I showed you with alkanes, you might have, especially when you have incomplete combustion, where you make carbon monoxide, CO, instead of CO2, most likely when that reaction happens in combustion, you're going to probably have a weird number of oxygens, and then you would probably have to have like a decimal or fraction on one side, but then you can go ahead and get rid of it by multiplying the whole equation by another factor to undo the fraction or decimal. And then you can go back and fix any other C or H that you might have messed up when you had changed that, fraction. And then, then you will have it balanced, okay? So it's not supposed to be too bad. This one, you did the carbon first, then you did the H, then you did the O, okay? Like what we've seen with the alkanes. So that we can get through very quickly. Okay, now, do you guys remember from a previous class your primary, secondary, tertiary alcohols? Do you remember? Kind of? The positions? Okay. In order to understand the first kind of reaction, okay. These are important for these positions of their OHs because depending on whether it's primary, secondary, tertiary, that will allow us to know how this oxidation reaction will proceed, okay? So if you remember, if you recall from your primary, okay, so that's basically where you have the alcohol connected to basically just a carbon that has two hydrogens, like this one, okay, and then for the secondary one, it's connected to a carbon, okay, with just one hydrogen, like as you see here, with my mouse disappearing. And then this one, the tertiary, you connect the OH to a carbon that is not connected to any hydrogens, okay? So that's the easiest way I can remember the difference between primary, secondary, and tertiary, okay? So this one, OH to a carbon with 2 H's. This is OH to a carbon with only 1 H, and tertiary, and OH to a carbon where this carbon is not connected to any hydrogen, okay? That's just the position where they are along the chain. All right, so for a primary alcohol, when it goes through oxidation, okay, it's going to go through a 2-fashion step reaction, okay? So let's break this down, what this all means. Now, you see this in your textbook on cognitive, kind of in symbolic representation of how it happens. So let me dissect for you what this all means, like the way it's written like this, because this doesn't show you the structure at all. It's just like a shortcut way to remember what's going on step by step, okay? So in your 2 steps here with the primary alcohol, so basically you have, as a catalyst, we have an oxidizing agent, okay? And we use that symbol bracket and O, okay? That's all that means. Bracket and O means the oxidizing agent. And then we will also heat it up at that stage, okay? And this oxidizing agent here is going to usually be an acidic version of potassium dichromate, okay? So basically here, it should be KCr2 or K2Cr2O7, okay? And then so Cr2O7, the polyatomic ion, it would have a charge of 2-, and then with a K2 to balance that out. So the original complete oxidizing agent compound is potassium dichromate, okay? But in this situation, you don't need to write it on your test, the K part, because the potassium would just act as a spectator ion, okay? And then we don't have to really worry about it in being a part of our condition for the oxidation. All right, so that's just the first step. Now, with that first step, the first thing you make is an aldehyde, okay? So we are, with just the first step, you make an aldehyde. And then once we form that aldehyde, if we go further, okay, using the oxidizing agent again, and then this time we will heat it in a special way. The second step, if I'm going to go further and make a carboxylic acid, this is going to be what we call a reflux. Okay, so give me a second. Let me show you a picture of that from the internet, what that looks like. This is kind of a reflux, okay? So all it is, it's like the condenser part of a distillation setup. Who did distillation in this lab, by the way? Nobody? I thought someone did distillation. No, that was grade 10, never mind. Okay. They were doing organic chemistry. Okay, so I had one student in grade 10 do this reflux. So basically all it is, it's a vertically placed or aligned condenser. So it just, usually, yeah, it's just flipped. Usually it should be horizontal, okay? That's what it is. And so what happens in this thing? You boil it to a point where you get the gas part to condense into liquid, and it's just like a cycle, okay? We'll get to that a little bit more in detail later, what the reflux is like. Right, so let's go back to my PowerPoint again. All right, so that, can you still see the screen? I hope so. All right, so then for this step, yeah, you're using the reflux, whatever, like condenser, and you heat it again, and then you use the oxidizing agent again, okay? The same one. So, and then you make your carboxylic acid. Now, I showed it down here when it was an alcohol like this. As an aldehyde, this is what you have. C double bond O and H. Then as a carboxylic acid, you will have then C double bond O, and then also a single bond to an O, and then H, okay? So that's just kind of a very shortcut version of step-by-step, these 2 steps in the primary alcohol oxidation, right? Now, what is this thing here, okay? So when I'm talking about this, okay, in this reaction, okay, the dichromate part, okay, it starts off at red color, okay? And as it oxidizes, okay, it goes to orange, and then it changes finally to a green. By the time it gets to a green color, it will become a chromium 3+ ion, okay? So if you forget that, I mean, it's not quite a traffic light. It should be really red, yellow, and green, but whatever, okay? But you don't really see yellow when you do the actual lab. You see an orange in between red and green. So, you know, I kind of made it analogous to a red light, but it's not quite there, okay? So remember, it's red, orange, green. And that's really some colors that you would be asked to recall on the multiple choice in your paper 1, okay? They will ask you to like pick the ABCD of the right sequence of the colors from dichromate to a chromium 3+, okay? So that's a question on paper 1 right here. Okay, so that is the primary alcohol. Let's go on to a secondary alcohol from up here, okay? So with the secondary alcohol, okay, you will oxidize it only one step. And now this time I'm going to, okay, you need an oxidizing agent again, okay? And then you do it this time with a reflux at this one single step. And then you will make a ketone. And then of course, remember your ketone looks like this, a C double bond to an O, just that kind of arrangement, okay? Usually in the middle between the chain, right? So that is your secondary alcohol oxidation. And then again, you still use for the O oxidizing agent, the KCr2O7, okay? So that's still the same, but you do it with a reflux in this single step. Right, that should be it now. The last one, your tertiary alcohol up here. This is not going to be oxidized at all by your potassium dichromate, okay? Now, the reason for this is that, okay, this tertiary carbon, if you see it here, it already has, do you see this? How many methyl groups is it attached to, everybody? 3, okay? So it's already attached to 3 methyl groups around it, not attached to a single hydrogen, that carbon, okay? So it's not so easy for these to be broken, these bonds between that carbon and the 3 methyl groups, okay? So then because it's too difficult to break, I mean, it's not that it won't ever happen. If you really give a really extreme conditions, it could be oxidized, but for S standard level, you're not expected to know what's going on if it ever got oxidized, okay? So ignore it because it has to go to much more higher conditions to be able to break these 3 like methyl group branches around, okay? So for now, you don't need to know that. And then you just don't worry about the mechanism of what happens with tertiary alcohol, okay? So you can just cross that out. Okay, so this is basically just showing, you know, in like this is condensed formula structure. You guys remember condensed formula is just like a, you lump them all. That would have been like C and then H, 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 right? This would be C and then H up here, H down here, okay? So then you need to be familiar with how to show it in a condensed formula way too, not just on the IB test. I can ask for either this version or this condensed version, okay, with the condensed formula. So be prepared to be able to do either way. But anyways, when you show it, okay, if you do it a condensed formula, it's a little bit easier, okay? You just have to make sure you keep track of the correct subscripts, right? And then what you do is to show your oxidizing agent, I want you to show it like this. It's acidified oxidizing agent, acidified potassium dichromate. So you could just easily write that as an H plus to show that it's acidified. And then over the dichromate part, we don't care about the potassium, okay? Then put heat under it, make sense? Okay, and here's a condensed formula for your aldehyde, okay? Null, A-L, by the way, that's not O-L, A-L. Okay, so that's the condensed formula for your aldehyde. And then again, if you do it one more step, then you show another arrow, do it H plus again for acidified, then show your chromate, dichromate, I mean, ion. And then this time, instead of writing heat, you write reflux. It is also heated, but it's in a special reflux, you know, condenser. And then again, it's oxidation, both of them. And then your condensed formula for the carboxylic acid, which will be then written as ethanoic acid. Make sense? Okay, so then this is the condensed version of those two steps for your primary alcohol. Got it? Okay, and then here is doing the secondary alcohol with a condensed formula. Then I also showed you here again too with the written out structure. Okay, so this is the equivalence of that one, but done condensed. Again, you write it like this, acidified with the dichromate ion. And then instead of writing heat, you basically do like this step, just do reflux. And then here, okay, you write it out like this. Be careful here. This is what happens. So it looks almost like this, but then here we are having a, okay, double bond created because I'm making a ketone, right? This is my condensed formula for a ketone. So then this is knocked off, the H is knocked off, and you just have a double bond to the O. And then the rest of it is the same as before, okay? And then just that one change with the double bond. Okay, so that is how you're doing from your secondary alcohol into a ketone. More or less, okay? All right. Now yeah, okay, that's enough. All right. Okay, now this part here, back to the primary alcohol. Okay, I want to explain this because this is also in your textbook about how does it work with this distillation, okay? So let me see, I'm talking about here. We would have, okay, again, you write this shortcut like this one. And in distillation, do you remember, normally we use it to separate things based on boiling point difference, remember? And we do evaporation, and then the one that has a lower boiling point goes up, becomes a gas, so on, okay? Now, this one is different than, let's say, what you've seen in some other processes. Like obviously, if you were doing like seawater, and you were doing this one with that, then you would be reaching up to 100 degrees Celsius to get the water out, and then it condenses here, right? And then the water will condense once you have another chamber that has cold water to bring that gas water back to liquid water. And then what you will be collecting in here, in the other flask, the end flask, we call it receiving flask. So you need to know that, okay? Because on your test, they will ask you to separate what's going on. There's a distillation flask, which is your mixture that has different components mixed together at the beginning. But your receiving flask is the end point of your distillation where you collect your distillate. And your distillate is basically what that means is your pure, whatever it is you want, that it should be alone by itself and not other junk in it, okay? All right, so I'm going to use this distillation, okay, to extract some of this in your two-step primary alcohol oxidation, right? So let's see if I talk about this correctly. Right, so yeah, so basically all this goes down here in the mixture, okay? And then again, you could write like this. Now it goes up this fractionating column. And then look at this, the temperature is not going to be 100. I only need it to go to only 30 degrees, okay? Before then that would become a gas. And then this is cold water from a separate compartment. And then that will cool it down. And then you would have here, okay, your pure, mostly you would usually use it to get like a pure, it could be a pure ethanol, okay, the aldehyde here. Okay, that's usually as far as we go. I probably wouldn't just save ethanoic, okay? I would use it to separate for mostly my ethanol, the aldehyde. That's if I started off with ethanol, 2 carbon alcohol in this with some other stuff in it, okay? All right, and then, yeah, and the boiling point is around 30 degrees. Yeah, so that's really all you need to know that. Okay, now, looking in more detail, with this reflux, so you saw that earlier. Okay, this is a picture of it again. Okay, so in the reflux, okay, so you've got your boiling flask at the bottom, and at the top is then your, you know, sort of the condenser part of it. And then here, it's a little bit weird how it looks here. Okay, so basically, it's vertically aligned as a condenser. Boil the mixture for an extended period of time. Now, the thing is, the reason why when you do a primary alcohol oxidation reaction, why sometimes we don't really want to go too far to get carboxylic acid is because this reflux process actually takes a really long time, sometimes up to 6 hours, no, 6 hours minimum, okay? So that's a very long time. You would never do it here in the lab here, okay, in the IB. So because you have to go through much more, the next step of extreme conditions with this reflux here, okay, before you were able to get from aldehyde into the carboxylic acid. So that's really what you need to know there, okay, about like the primary alcohol reaction is if they ask you, why do you sometimes not want to collect carboxylic acid and you want to stop at the aldehyde, it's because it takes too long. The reflux process takes too long, okay? But anyway, so the mixture in here, like I explained it, okay, when you boil this mixture, okay, for a long time, it boils very fast, okay? There's a lot of bubbling that happens in this reflux, okay? And then lots of condensation will happen here, up higher, and then the gases will drip back down into the boiling flask, okay? And then hopefully what will come out that we get is what we want to have at the end. Some of it, anything we don't want will go away, and then whatever we want it back will come back down here. Hopefully the carboxylic acid that you wanted, okay, after 6 hours or more, okay? So that's really all you need to know is that, you know, it takes a long time, and then you will have some of it drip back down here, your carboxylic acid. Now, we can do it only if you have enough of your oxidizing agent, just so you know, okay? If you don't have enough of that dichromate, then you won't be able to make it to the many, many hours that it would take. So it has to be done with an excess amount of the dichromate. Okay, that's something that they'll ask you on the multiple choice section, okay? Where could it fail is if you didn't have enough of that catalyst, okay? And yeah, that's it for the reflux. All right, now we are going on to the last of the reactions for your alcohols, esterification, okay? So we're done with now combustion and oxidation. We're here for esterification. So first off the bat, are you all familiar with this from MYP? Did you ever make an ester in grade 10? Okay, well, esters are really fun. I had my grade 10 do it already. Basically, esters are the stuff that smells really nice. They use it for all these things. Anything that gives a lot of your major commercial products some distinct flavors and like nice smells or taste is because thanks to esters, all right? Esters can also be used for perfumes as well to give it like that additional smell. But anyways, that's really the application of why esters are very important, all right? But anyways, okay, I'm sorry, I think I'm having allergies. Now, so for esters, okay, so another group of your organic compounds, right? So with these things here, okay, they're small molecules, they're very volatile, okay? And so because they're small and they easily can reach your nose, okay? So, and because they become gas so easily, see what I mean? So, and that's why they often give the strongest smells because they're smaller molecules compared to other organic compounds that are able to travel around in gas form, okay? And then the smell just kind of permeates through everywhere. So that's why they work the way they do. But if esters of larger molecular size, then they usually would be in the form of oil and wax, okay? All right, so esters are made by having a reaction between your, sorry, that's a misspelling. There should be an alcohol and a carboxylic acid, okay? So it's between the carboxylic acid and an alcohol. And it goes through what we call a condensation reaction, okay? So it is going to require these two. And then basically what you're going to end up getting at the end, okay, is an ester and then a water that just kind of gets given off, okay? That's usually the main products that you get is an ester and H2O, right? So then what you're going to do is you need to understand the mechanism for the reaction between the carboxylic acid and the alcohol, okay? So this again, this part, if you remember from when we looked at the table of functional groups from a few lessons ago. So you should be able to identify where it is unique to identifying it as an ester, okay? All right, so when you are doing this, okay, so let me make sure I didn't make any mistakes here. Okay, did I knock off the water? Yes, I did. And then, okay, that's good. All right, so first off, you start off with your alcohol. Ethanol is your 2-carbon alcohol with the OH at the very end. Remember, okay? So put your OH at either end, doesn't really matter, it's symmetrical anyways, right? So then you have the ethanol, and then you have your carboxylic acid, your ethanoic acid as a carboxylic acid. Now, when you are, so it's this alcohol plus your formula for your carboxylic acid, okay? And then when you do the arrow, you will write that your main acid that you will use is concentrated sulfuric acid, okay? So you're going to use concentrated sulfuric acid as your catalyst. And you can always write that if you show it on your test as concentrated CONC and then H2SO4, right? So that's how you write that on your test. Okay, now then you will make an ester on this side. So what you would do is, what is happening is it's sort of a the alcohol and the ethanoic acid kind of join together, and then there's like 2 distinct parts on this entire big old ester molecule, okay? So you need to be able to know how to basically just connect them. So like here, it was an O and an H, and then that H will be plucked off, and then you kind of join this part here. So when you write it this way, sometimes you don't really write your carboxylic acid like that. You might usually do it with the CH3 and then C and then your double bond O and O. But for simplicity, why don't you flip it around a little bit so that the double bond is going to end up, because the double bond part of this carboxylic acid, what you want to have happen is write it in such a way when you show this mechanism, write the double bond here and then this single bond to the O here with its H here, because where the reaction is really happening is the H from the OH on the alcohol will get together with the OH on this part of the carboxylic acid. So then this H and O will form your H2O, right? That will make a water. And then that water will be just like another product here. And then whatever is remaining is the rest of it that you still have minus the H2O that already got knocked off, okay? And then that's how you form your ester molecule here, okay? And here the name we call it is ethyl-ethanoate. Now, when it comes to naming, it's not too tricky, but it's sort of, there's a very systematic way to name your ester. Okay, so if you look at this table, so from here, this is an easy way to do it. All you do is when you have, okay, you have your alcohol, you have your carboxylic acid, okay? When you name it together, if I have a methanol and methanoic acid, my ester name is going to be something like methyl-methanoate, okay? So what you're doing here, okay, from these things is where to replace the parts that were in your original alcohol name, okay, and your carboxylic acid name, okay? So like here, the ill replace this NO from the alcohol part, right? So an ethanol would have become ethyl, and then for the ethanoic acid, okay, so that whole part here will be replaced with OATE. Sorry, that should be OATE, okay? So that's the OATE, OAT part of that ester name. Okay, so going over here, so if I was to do methanol and methanoic, it becomes methyl, and then and then take out OIC acid, and it becomes OATE. Same thing here, ethanol with ethanoic becomes ethyl ethanoate. All right, and then you get the idea, but you can mix and match these as well. So if I did something like propanol and ethanoic acid, what would you think I would call it? Propyl what? And ethanoate, right? So you can mix and match these on this table when you do like the name of the ester product. So this would be propyl, right? And then ethanoate, okay? So any of these that could be in different combinations is how you decide to name that, okay? So yeah, so anyways, so this propyl methanoate would have been from propanol and methanoic acid. Make sense? To get propyl methanoate. That's the name of the ester. Okay. Now look when you draw it out here. Like when you draw it out here again, this one is like this one. And what I did here was esto butanoate. Okay. So look how I did this red line to divide where the alcohol portion is. This is everything up to the O. Make sense? And then the H would have been completely replaced by all this stuff from the carboxylic acid. And of course, it has 1, 2, 3, 4. So it would have been the butanoic acid, right, for 4 carbons. But then now here's the butanoate. And the SO is coming from 2 carbon alcohol, okay? And that's it. That's your ester molecule here. I hope I didn't lose anybody. Okay, now you can do the same thing, okay, with condensed formula, just like I asked you earlier before. So not only do you need to know how, okay, sorry, I'm skipping ahead of time. We didn't even do this one yet, okay? This is how you create ester propyl, okay, butanoate. So I start off with this one. This would have been a 3 carbon alcohol, right? That's the propyl part. And then this OH will react with, if I draw this carboxylic acid with the double bond on the left side, so that that OH can react with the H from the alcohol. So then this H2, H and HO will become H2O that I just write over here. Make sense? And then here, then you start to just connect them like this. This is the alcohol part. I wrote H2SO4 over here. You have to write concentrated, by the way. Concentrated H2 is SO4, okay? But I just lazy, so whatever. Now here, 3 carbons is coming from that alcohol. And then you have the O, and then all that H is replaced by whatever came from my 4 carbon carboxylic acid, okay? And then here, I could have put the O double bond up here. It doesn't really matter, okay? I just wrote it down here. And then the rest of it is all connected to hydrogens. The rest of the carbons are connected to hydrogen. You just fill in the hydrogens where you can, okay? So that's how you do that part there. Okay, now, this is the same thing as I did up here. Okay, so when I write it in condensed formula, this is CH3, CH2, CH2, and then here was OH, what it used to be. And over here, okay, then be careful how you do the condensed formula here. This is your HOOC, oh, sorry, okay. And then this part is another CH2, CH2, CH3, okay? And then arrow, concentrated sulfuric acid, and then here's the condensed formula of your ester, okay? So CH3, CH2, CH2, O, then you can do O again here, and then the carbon, and then another CH2, another CH2, and another CH3. And then dump water at the end, the other product, okay? And then the final question that you will probably be asked is, if you were given this structure and you need to identify the ester functional group, just circle that part here, right? So that's the ester functional group there. And then, yeah, so that's pretty much it. So that is your lesson on alcohol reactions, right? So I think, are we out of time yet? Oh, okay. So tomorrow we will finish up with halogen alkanes and benzene reaction, okay? That will end completely 10.2 in the topic 10 standard level. Oh, let me stop this video so it's not going to be too long. Stop recording.